All right. Welcome to our second video for this week. We are going to continue talking about our indexed sets. But let's talk about something called pairwise disjoint. Pairwise disjoint, a collection is pairwise disjoint. So that's a set of all sets, a set of sets, right? Which we're allowed to have. We call it a collection of sets instead of set of sets, just to make that more clear. It's pairwise disjoint if every intersection between any two pairs is the empty set. Okay, what the heck does that? So let's look at this just real quickly. Essentially, if I did this visually, here is set A alpha. Here is set A beta. I have to draw them so they don't intersect at all. If I draw another set, it cannot intersect with any of them. So it has to be completely separate. So it has to be A, let's go gamma. And I can continue on and create whole nother sets, but they have to each one have zero intersection, no element in common between them. Now, I just did a Venn diagram. What would that look like if they're disjoint? And we just talked about that. I just drew that picture. They're three separate circles that do not overlap. But I want you to try to do an example with that in mind now. Suppose I tell you I want you three sets. So the collection is not pairwise disjoint, but the intersection of all three is empty. What would that look like if you have, so in other words, if it's not pairwise disjoint, let's go back to the definition of pairwise disjoint. If the pairwise disjoint is every pair is the empty set, what is not pairwise disjoint? And this is an example. So this isn't a generalization. You can literally come up with an example, with a couple things being shared, but you have to create it in a way that the intersection of all three of them is the empty set. All right, now let's talk about a theorem that is a little bit harder, and I want you to think about this one, and I want you to try to prove these things right here. These are going to be a little bit harder because you're trying to talk about these things in super generality. So again, this is not, so while you did an example for the previous problem, this is going to be a general proof, and there's two parts. So the first one, part one, let's take the intersection of my entire collection. All right, so I have the intersection of my collection, and I'm going to union that with a set B, where B is any set. And I'm saying that is equal to the intersection of B union with every single one of those sets in the first place. And how would you prove this? Remember, the way we usually prove this is we claim that something is an element. To show equality, I'm going to show that I'm going to have to do two sides of this. So I'm going to need it. So the first one, just a quick remember. So I'm going to write this down. For number one, I'm going to need to show that B union alpha contained in delta, A alpha, I'm going to have to show that's a subset of the intersection of alpha contained in delta of B union A alpha. And then, so this is actually part one. And then you have to do part two. I know I have slight slant. I apologize for that. I'm essentially going to do the same thing, except I'm doing the opposite direction. So I'm making it a superset. Now, what's that mean? Again, so let me just finish writing this down of what we're trying to show for part one. So really, I'm asking you to do this. I'm asking you to do 4 proofs here. I know that's a lot I'm asking, but you all can handle it. I think you can. So for the first one, you're going to start, all you have to do is let's let X be some element that's in here. I need to show that that element is over here. So we're going to start with showing an element of the left-hand side is an element in the right-hand side. That's one of the major things that we do with proofs is we say, whatever the subset, I'm just like, suppose that I have an element in the subset. You could also do this, and I believe Cameron did this a couple discussion boards where she actually did the opposite. So she did the contrapositive, which was suppose an element's not in the larger set, then show it's not in the smaller set. That also works. So in other words, to show the second part, I can say that suppose that X is not an element of the right-hand side, and then show it's not an element of the left-hand side afterwards. So there's multiple ways to get about this. So I want you to prove this. So your two problems to work on are you're going to find an example, and then you're going to prove this one, which is really a 4-part proof, and it is going to be kind of bigger, but you can do it. All right, let me know what questions. I'm excited to see what y'all come up with this week. Good luck.